Dear students, my name is Pankaj and welcome to my channel Maths with Pankaj sir. Here we are going to cover all the important chapters for JEE mains in mathematics from basics to advanced. And today we are going to start complex numbers. We are going to cover this chapter in 4 to 5 sessions. So today is session 1 of complex numbers. The problems that I will be taking will be a bit complex and it will cover the questions will be cross topic, so you should have knowledge of other chapters as well, like basic knowledge. We know at least one or two questions are always there in JEE mains from complex numbers, and complex numbers is generally combined with integration and many other chapters as well. So there are cross topics questions from complex numbers, so you must have a deep understanding of the topic. So we will be from the start itself we will be taking complex examples, tough examples, to make you understand, to make you realize the depth of the topic. We will be covering the concepts from basics to advanced, but for examples I will not be explaining easier words. I will not be wasting your time. I will be directly taking you into the depth so you understand better. So in this session we will be covering what are complex numbers, algebra of complex numbers, integral powers of iota, conjugate complex numbers, and representation of complex number on Argand plane. So let us now understand what are complex numbers. The basic definition of complex number is any number of the form a plus iota b is a complex number where a and b belongs to real numbers. Now this I is called iota and its value is always root of -1. So we can also say that any number in this whole universe is a complex number. If you ask me, are these all real numbers complex numbers? Yeah, that's true. And all the imaginary numbers are also complex numbers. So you all know real numbers. Let us now understand what are real imaginary numbers. So complex number are divided into two parts. One is real numbers and or you can say real part, and other one is imaginary part. So to understand what are imaginary numbers and what is imaginary part, we will take an example. So to understand, let us move to next slide. Suppose you have a equation x square plus 1 equals to 0. From this equation you get x equals to root of -1. So clearly it can be seen that x is not a real number. Not a real number. Therefore, we call it as imaginary number. We call it as imaginary number. And this value x equals to root of -1, this value is known as iota. So this value is known as iota, which is denoted by small I, and its value is root of -1. So if I ask you what is iota square, so it is obvious iota square is -1. Then if I ask you what is iota cube is iota square into iota. We all know iota square is -1, so it becomes minus iota. Iota raised to 4 is square of iota square, so obviously it becomes 1. And again if I ask you iota raised to 5, this is iota raised to 4 into iota. Iota raised to 4 is 1, therefore it is iota only, and so on. Now if you see the pattern, see iota raised to 1 is iota only, iota square is -1, iota cube is minus iota raised to 4 is 1, and again iota raised to 5 is iota. So as a conclusion, if I ask you what is iota raised to 4k, so you will say, sir, this is iota raised to 4 to the power k. And we all know iota raised to 4 is nothing but 1. We all know iota raised to 4 is 1. So this becomes 1 raised to k, which is 1 only. Fine. What if I ask you iota raised to 4k plus 1? So you will say, using property of indices, this is iota raised to 4k into iota. So this becomes iota raised to 4k is 1. So this is iota. And iota raised to 4k, similarly, it becomes iota square, which is minus 1. And iota raised to 4k plus 3 is minus iota. How? Since this can be written as iota raised to 4k into iota cube. We know iota raised to 4k is 1. This value is 1, and iota cube we have already calculated. So iota cube is minus iota. Iota cube is minus iota. So I can directly write 1 into minus iota, which is minus iota. Somehow you have to memorize these facts, these conclusions. I raised to 4k is 1. 4k plus 1 is iota. 4k plus 2 is minus 1. Iota raised to 4k plus 3 is minus iota. You have to memorize these. And now I'm going to write few more properties and few more facts that you need to remember. If I ask you, so as an example, if I ask you what is iota raised to 12, so you will say, sir, 12 is multiple of 4, so I can directly write it as 1, because we know iota raised to 4k is 1, and where k is an integer. If I ask you what is iota raised to 16, so again this is 1. So if the power is multiple of 4, then definitely iota raised to that power is going to be 1. Next, if I ask you n equals to 1, 2, 4, iota raised to n, so this becomes iota raised to 1 plus iota raised to 2 plus iota raised to 3 plus iota raised to 4. Okay, before solving this problem, let me explain to you one more property, which is if you add up all these iota raised to 4k plus iota raised to 4k plus 1 plus iota raised to 4k plus 2 iota raised to 4k plus 3, you will get iota raised to 4k is 1, 4k plus 1 is iota, 4k plus 2 is minus 1, minus iota. So everything cancels out. 1 minus 1, 0. Iota minus iota, again you get finally 0. So I can write as a note, most important, I can write as a note sum of four consecutive powers of iota is always 0. This is most important. You have to memorize this fact that sum of 4 consecutive powers of iota is always 1. As an example, I can say iota raised to 5 plus iota raised to 6 plus iota raised to 7 plus iota raised to 8 will always be 0. This is always true. Again, iota raised to 198 plus iota raised to 199. I can start with any number. Iota raised to 200 plus iota raised to 201 is also 0. The sum of four consecutive powers of iota is always 0. Now, in this question, iota raised to 1, 2, 3, and 4. Sum of four consecutive powers of iota. This will give you 0. So, if I write summation n equals to 1 to 4k iota raised to n, so this will always be equal to 0. This is the important fact that you have to remember. But also remember, do not make mistake that summation, if it is given n equals to 0 to 4k and iota raised to n, this is equal to 0. So this is not true. See, here in this above property, we have n equals to 1 to 4k, n equals to 1 to 4k. So how many terms are there from 1 to 4k? So there are 4k terms. And here in this part, we have 4k, we have 4k plus 1 terms. So in this case, we have one extra term that will not lead to 0, one extra term. But in above case, you have proper pairs of four consecutive powers that would lead up to 0. So this is something that you need to remember. Star mark. So as of now, you have studied two properties of integral powers of iota. One is summation of n equals to 1 to 4k, iota raised to n is 0, and iota raised to 4k is always 1. Iota raised to 4k is always, so I'll write it alongside this. Iota raised to 4k is always 1. You have to remember this as well. Complex number a complex number has two parts, real and imaginary. Complex number is generally denoted by z, and usually we write z equals to x plus iota y. Usually this is the expression that is used to denote a complex number, z equals to x plus iota y, where x equals to real part of z and y is known as imaginary part of z, and x and y both belongs to real numbers. So as an example, if I ask you, I have z equals to 2 plus 3 iota. So if I ask you what is a real part of z, it is 2. And if I ask you what is imaginary part of z, it is 3. Now let us understand what happens when x, which was real part of z, becomes 0. Our complex number becomes iota y. So this is known as purely imaginary complex number. So whenever a complex number is said to be purely imaginary, its real part is always 0. Similarly, if the imaginary part which is y of a complex number is 0, then z equals to x, and this complex number is known as purely real complex number. So whenever a complex number is given to be purely real, then its imaginary part is always 0. This is something we need to understand. Purely imaginary and purely real. Whenever the real part of a complex number is 0, then the complex number is purely imaginary. And when the imaginary part of a complex number is 0, then the complex number is purely real. Simple. Now let me summarize what we have learned so far. First of all, iota raised to 4k is always 1. Important. Summation n equals to 1 to 4k iota raised to m is always 0. And and purely imaginary complex number x equals to 0, purely real complex number y equals to 0. One more basic topic before solving questions I have to explain to you, which is rationalization of complex numbers. Rationalization of complex numbers. So first of all, let us understand what is rationalization. Whenever you eliminate radicals or imaginary numbers from the denominator, whenever you eliminate radicals or imaginary numbers from the denominator of a fraction, this is known as rationalization. Of a fraction is known as see, this topic is generally introduced after algebra of complex numbers when we already studied like addition, subtraction, multiplication, and division of complex numbers. Then we study rationalization of complex numbers. But I'm introducing it earlier because in earlier classes, like in class 9th and 10th, you have already rationalized radicals. So first of all, if you have something like root 1 upon root 5 minus root of 2, and you have to rationalize this, so you will multiply the fraction with root 5 plus 2 upon root 5 plus root 2, which will again be equal to root 5 plus root 2 upon a plus b into a minus b is a square minus b square. So this becomes root 5 plus root 2 upon 5 minus 2. So as you have already studied rationalization of radicals, you have already studied this, I hope, I expect this from you. So that is the reason I am introducing this rationalization of complex numbers, and so that we solve some good examples and good questions on this concept. And finally, this reduces to root 5 plus root 2 upon 3. So we have eliminated radical that was root 5 minus root 2 in the denominator initially, and now our denominator is 3, which is an integer. Similarly, what if the denominator is an imaginary number? For example, 1 upon 2 plus 3 iota. So what we will do is, we will simply multiply 1 upon 2 plus 3 iota with its conjugate. You will understand what is a conjugate later. We will also study properties of conjugates. But for now, बस इतना समझ लो. If I have to rationalize this, so I will multiply it by the conjugate, which is 2 minus 3 iota, and divide by 2 minus 3 iota. Similarly, that we have eliminated radicals. Now this becomes 2 minus 3 iota upon 2 square, which is 4, minus 3 iota square, which becomes 2 minus 3 iota upon 4 minus 3 square is 9, and iota square is minus 1. So 4 plus 9 is 13. So 2 minus 3 iota upon 13. This is rationalized form. This is rationalized form in which we have eliminated imaginary number from the denominator. So now I am left with iota raised to 4n plus 5 plus iota raised to 4n plus 6 plus iota raised to 4n plus 7. So if I take iota 4n common, iota raised to 5 plus iota raised to 6 plus iota raised to 7. Clearly I can say iota raised to 4n is 1. This is 1. And iota raised to 5 is iota raised to 4 into iota, which is iota itself. Iota raised to 6 is iota raised to 4. See, iota raised to 6 is iota raised to 4 into iota square. So I can write it as minus 1. Iota raised to 7 is nothing but iota raised to 4 into iota cube. So which is minus iota. So this becomes iota minus iota is 0. So final answer is minus 1. Let's see another example. This is, I think, the most trickiest question. So in this question we are asked, what is summation n equals to 0 to 100 iota raised to n factorial. It simply means iota raised to 0 factorial plus iota raised to 1 factorial plus iota raised to 2 factorial plus iota raised to 3 factorial plus iota raised to 4 factorial plus iota raised to 5 factorial plus iota raised to 100 factorial. So let me tell you what is factorial. 3 factorial is 3 into 2 into 1. 4 factorial is 4 into 3 into 2 into 1. 5 factorial is 5 into 4 into 3 into 2 into 1. I can clearly say 4 factorial, 5 factorial, 6 factorial, and so on. 100 factorial. All are multiple of 4. And using I raised to 4k is always 1. So therefore iota raised to 4 factorial is 1. Iota raised to 5 factorial is also 1. and iota raised to 100 factorial, this is also 1. 4 to 100, we just have to calculate how many terms are there from 4 to 100. So for calculating number of terms, we will simply write number of terms is 100 minus 4 plus 1, which is 97. So these are terms from 4 to 100. So now let us solve some examples on the concepts that we have learned right now. In this question, we have to find the value of summation n equals to 1 to 13 in plus iota raised to n plus 1. There are two methods that we can use to solve this problem. So we will see those two methods. Here I'll solve with method 1, and on the right hand side method 2. So in method 1, I will take iota raised to n common, so I am left with 1 plus iota. As 1 plus iota is independent of n, so I can take it out of the summation, and now I am left with 1 plus iota n equals to 1 to 13 I raised to iota raised to n. We know that summation iota raised to n and n is from 1 to 4k, this value is always 0, because sum of 4 consecutive powers of iota is always 0. So obviously summation n equals to 1 to 12, as 12 is multiple of 4, iota raised to n is always 0, which gives us this value 1 plus iota into iota raised to 13, because 1 to 12 summation is 0, and iota raised to 13 can be written as iota raised to 12 into iota. Now we know that iota raised to 4k is always 1, as 12 is multiple of 4, so we can say that this value iota raised to 12 is also 1. So I can write it as iota plus iota square, which is iota minus 1. This is my answer. So if I solve this using method 2, I will just split the summation, and I will write summation n equals to 1 to 13 iota raised to n plus summation n equals to 1 to 13 iota raised to n plus 1. So again, using this property which I have used earlier, 1 to 12 it is 0, so I am left with iota raised to 13 only, and here again I am left with 13 plus 1, which is iota raised to 14, which gives me, as iota raised to 12, if I take common, I am left with iota plus iota square, and we have already as it is already known that iota raised to 12 is always 1, as 12 is multiple of 4, so I can write it as iota plus iota square, as iota raised to 12 is 1. So my final answer is iota minus 1. So this was one application of integral powers of iota. We will see some few more examples. See, we are asked summation r equals to 1 to 4n plus 7 iota raised to r. See, using above properties, I can clearly say that r equals to 1 to 4n plus 4 is I raised to r is always 0, because sum of 4 consecutive powers of iota is always 0, and 4n plus 4 is multiple of 4. Now the summation reduces to n equals to 0 to 100. Iota raised to n factorial is now reduced to iota raised to 0 factorial, which is 1. Iota raised to 1 factorial is again iota. Iota raised to 2 factorial is iota square. Iota raised to 3 factorial is iota raised to 6, plus 1 plus 1 plus 1 97 times, so this is 97. I can write it as 2 iota plus iota square is minus 1, and iota raised to 6 is also minus 1. See, iota raised to 6 is iota raised to 4 into iota square. This is 1, so iota raised to 6 is iota square, which is minus 1, plus 97. So this gives us 95 plus 2 iota. This is our final answer. Let us understand. Okay, now look at this question. In this question, we have to show that the polynomial x raised to 4p plus x raised to 4q plus 1, 4r plus 2, 4s plus 3 is divisible by 1 plus x square plus x cube. See, 1 plus x square plus x cube. If I have to find sum of all these, first understand 1 plus x square plus x cube, this forms a GP, geometric progression. So if I have to find sum of this, it is x raised to 4 minus 1 upon x minus 1. Sum of GP is let me tell you, sum of n terms of a GP is a into r raised to n minus 1 upon r minus 1. Here in this case, a is 1, r equals to x, and n is number of terms, which is 4. That's why I have written x raised to 4 minus 1 upon x minus 1. So if I further extend this, it can also be written as x square minus 1 into x square plus 1 upon x minus 1. Further, x square minus 1 can also be written as x minus 1 into x plus 1. I hope everyone have memorized all the algebraic identities so far. So now I have x plus 1 into x square plus 1. I can further extend x square plus 1 as x plus iota into x minus iota. Now, from this point onwards, you need basic knowledge of factor theorem and remainder theorem of polynomials. Factor theorem of polynomials. See, if x plus 1 is factor of px, then p of minus 1 must be equal to 0. Therefore, we will have to find p of minus 1, p of minus iota, and p of iota, and then we will have to check if all of them are equal to 0, then definitely this polynomial is divisible by 1 plus x square plus x cube. So if I substitute minus 1 raised to 4p plus minus 1 raised to 4q plus 1 minus 1 raised to 4r plus 2 minus iota raised to 4q plus 1 and minus iota raised to 4r plus 2 minus iota raised to 4s plus 3. These values using properties gives us 1 plus this is a minus 1 into iota raised to 4q plus 1. So iota raised to 4q plus 1 is always iota plus iota raised to 4r plus 2 is iota square and minus iota cube, which can further be written as 1 minus iota minus 1 and plus iota, which on simplification gives us 0. And similarly, p of iota, if you will calculate, this is your homework, this will also give us 0. So solve this, and as all these values p of minus 1, p of minus iota, p of iota gives us 0, therefore x plus 1, x plus iota and x minus iota all are factors of x raised to 4p plus x raised to 4q plus 1 x raised to 4s plus 3. Hence it is divisible by 1 plus x square plus x cube. Hence proved. Now let us understand this example. For real theta such that 3 plus 2 iota sine theta upon 1 minus 2 iota sine theta is purely real and purely imaginary. So first we will solve for purely real. But before that we will have to rationalize it, and we will have to remove complex number from the denominator. So we will multiply it with the conjugate 1 minus 2 iota sine theta into 1 plus 2 iota sine theta divided by 1 plus 2 iota sine theta, which is equal to 3 plus 6 iota sine theta plus 2 iota sine theta into 1 and 2 iota sine theta into 2 iota sine theta, which is 4 iota square sine square theta divided by 1 minus 2 iota sine theta 1 plus 2 iota sine theta, which is a square minus b square. B square is 4 iota square sine square theta. If you solve this, it becomes 3 iota square is minus 1, so 3 minus 4 sine square theta plus, if I take iota common, so now I am left with 4 iota sine theta and 2 iota sine theta. It becomes plus 8 iota sine theta divided by iota square is minus 1, so this becomes plus minus 1 square is 1, iota square is minus 1, so it becomes 1 plus 4 sine square theta. This can be written as 3 minus 4 sine square theta upon 1 plus 4 sine square theta plus iota 8 sine theta upon 1 plus 4 sine square theta. This acts as x and it is y. So for purely imaginary, or sorry, for purely real, y is 0, imaginary part is 0. So I can write 8 sine theta upon 1 plus 4 sine square theta is 0. Therefore 8 sine theta equals to 0, sine theta equals to 0, theta equals to 0, theta equals to n pi, where n belongs to integers. For purely imaginary, Clearly, real part is 0, x is 0. So I can write it as 3 minus 4 sine square theta upon 1 plus 4 sine square theta will be 0. So 3 minus 4 sine square theta will be 0. Sine theta will be plus minus root of 3 by 4. Root 3 by 2. So theta value will be so theta value will be so theta value will be 60 degree, which is pi by 3 and minus pi by 3. So for this you must have basic knowledge of trigonometry as well. I told you earlier that we will be covering chapter to the depth of the topic, so you realize the complexity of this chapter. And now we are going to now let's get back to another example. This is also interesting example. 1 plus iota 1 minus iota raised to n equals to 2 upon pi sine inverse 1 plus x square upon 2x. So we all know that range of sine y is always minus 1 to 1. So let y equals to sine inverse 1 plus x square upon 2x. Therefore sine y equals to 1 plus x square upon 2x. So if range of sine y is minus 1 to 1, then obviously 1 plus x square upon 2x, its range will also be from minus 1 to 1, which gives us 1 plus x square upon x 2x is less than equals to 1, which in turn means 1 plus x square minus 2x is less than equals to 0, which means 1 minus x whole square is less than equals to 0, which in terms, as value of whole square can never be negative, so we have to understand that 1 minus x whole square is equal to 0, as it can never be negative. Therefore x equals to 1. For x equals to 1, this value becomes this function becomes 2 upon pi sine inverse 1 plus 1 upon 2, which is 2 upon pi sine inverse 1. As we all know that sine pi by 2 is 1, so 2 upon pi into pi by 2, which is nothing but 1. So now I can write 1 plus iota upon 1 minus iota raised to n is nothing but 1. Using rationalization, we can also obtain using rationalization we can also obtain now we can rationalize this number 1 plus iota upon 1 minus iota as 1 plus iota into 1 minus iota upon 1 plus iota into 1 plus iota. I can write it as 1 plus iota square upon 1 minus iota square, which will be 1 plus iota square plus 2 iota upon 1 minus minus 1, which is 2. Iota square is minus 1, so this will cancel out, and finally we are left with iota. So always remember, let me star mark this. You have to memorize iota plus 1 upon 1 minus iota is always iota. So now this gives us iota raised to n as 1. Therefore n will be 4. So least possible value of n for which iota raised to n is 1 is 4. In this question we are given x square p plus iqx plus 3 iota is 0. So if we have a quadratic equation, it will require knowledge of quadratic equations. Sum of roots is minus b upon a, and product of roots will be c upon a. It is given that sum of the square of roots is 8. So first of all, let the roots be alpha and beta. So clearly alpha plus beta sum of roots is minus b upon a, which is minus of p plus iota cube upon a, which is 1, and product of roots alpha beta is 3 iota. C upon a is 1, so alpha beta equals to 3 iota. Now it is given that sum of the square of the roots is 8. So I can write it as alpha square plus beta square can also be written as alpha plus beta whole square minus 2 alpha beta equals to 8. So if I substitute these values of alpha plus beta from equation 1 and alpha beta from equation 2, I get p plus iq whole square as minus 1 square is 1, so I have removed it, minus 2 alpha beta, which is given 3 iota, is 8. So it can be written upon expanding p square plus iota square q square is, I am writing it directly, p square minus q square plus 2ab, which is 2pq iota minus 6 iota equals to 8. P square minus q square, if I take iota common, I have 2pq minus 6 equals to 8. It is clear 8 can also be written as 8 plus 0 iota. Now, on comparing left hand side and right hand side, I can write p square minus q square equals to 8 and 2pq minus 6 equals to 0. This implies pq equals to 6 by 2, which is 3. So p equals to 3 upon q, or q equals to 3 upon p. So I can substitute any of the value of p or q, which becomes p square minus 9 upon p square equals to 8. If I substitute q, value of q, clearly I can see p is either clearly p can be either plus 3 or minus 3. This implies q equals to 3 upon p, q equals to plus minus 1. Answer. Let us solve one more question. If z equals to 4 plus iota root 7, then find the value of z cube minus 4z square minus 9z plus 91. It is given that z is equal to 4 plus iota root 7. So I can write z minus 4 will be equal to iota root 7, squaring both sides. I can write z minus 4 square will be equal to 7 iota square, z square plus 16 minus 8z equals to minus 7. Z square, this implies z square minus 8z, and if I take 7 on this side, this will give plus 23 equals to 0. So if I divide the polynomial px, which is a z cube minus 4z square minus 9z plus 91 with this quadratic polynomial z square minus 8z plus 23, four z square minus 9z plus 91, and we will divide first term of this dividend with first term of divisor, which gives us z. Here it will become z cube, z into minus 8z square and 23z. Upon this will become minus plus minus. Z cube cancels out, minus 4z square plus 8z square, which becomes 4z square minus 9z minus 23z. It becomes minus of 32z. Now first term of divisor gives us 4. So plus 4, and it becomes 4z square minus 8 4 is 32z, and plus 4 3 is 12, 23, 4 3 is 12, 4 2 is 8, and 92. Again minus plus minus, so this cancels out, even this cancels out. Now 91, and I have plus 91 minus 92, so I am left with minus 92 plus 91, which indirectly gives me minus 1. So I can write using a dividend equals to divisor into quotient plus remainder. This is dividend, this is divisor, quotient, and this is remainder. So I can write z cube minus 4z square minus 9z plus 91 equals to z square minus 8z plus 23 into z plus 4 minus 1. We know that z square minus 8z plus 23, it is given to be 0 from equation 1. So if this is 0, then the given polynomial px becomes equals to minus 1, which is your answer. Now let us solve this example. Let z be the complex number satisfying the equation this, where m belongs to R real numbers. Suppose the equation has real root, then find the value of non-real root. So let alpha be the real root. Hence we can write alpha square minus 3 plus iota alpha plus m plus 2 iota is 0. Separating iota terms, I can write alpha square minus 3 alpha plus m plus iota. If I separate iota, it becomes minus alpha plus 2 equals to 0. Using equality of complex numbers, alpha square minus 3 alpha plus m equals to 0, and or you can say minus alpha plus 2 equals to 0, which gives us, sorry, it is and, which gives us alpha equals to 2. Also, product of roots is c upon a, which is m plus 2 iota. but we don't have value of m. So from this equation, alpha square minus 3 alpha plus m equals to 0. We will have 2 square, which is 4, minus 3 to the 6 plus m equals to 0. So 4 minus 6 is minus 2. This gives us m equals to 2. Therefore, therefore, product of roots alpha into beta will be 2 plus 2 iota, or I can write it as 2 into 1 plus iota. It is given that one of the real root alpha is 2, so 2 into beta is 2 1 plus iota. Therefore, the non-real root is 1 plus iota. Answer. So this was an interesting question using equality of complex numbers. Okay, so dear students, time has already crossed 1 hour, so I will have to end this video for now, and I will continue the same in the next lecture. I hope you liked it. मिलते हैं अगली वीडियो में. Thank you so much.